Thank you so much. I'm really glad to be with you. Of course, would love to be in the room with you, but I'm glad that we can do this remotely. I am going to be talking about audiovisual learning from the computer vision perspective, and in particular in terms of spatial sensing. And so thinking about AV or audiovisual learning in 3D environments. So I'm going to start with a video. And it's going to illustrate really well what we need to be thinking about when we talk about audiovisual learning in 3D spaces. And that is the influence of room acoustics on what we're going to hear. So I hope you could hear the dramatically different sounds you receive according to where those drums were playing. Of course, it was the same kind of physical drumming sequence, but played in all these different spots where, depending on the geometry of the space and the materials of its major surfaces, you get a very, different sound. The amount of reverberation and how you receive that sound, it just varies. And okay, so we know that's true about our human perception. And then the question is, why is it important to note this? And why should we be modeling it and learning about it in our AI models? And so there's two big domains where I think this becomes so important. On the one hand, you have augmented reality or virtual reality, where we want to be able to have truly immersive experiences for people and transport them to new environments and mixed environments. And this calls for having that true realism of place. And so to do that kind of generation or resynthesis, you need to account for these scene and room acoustics. And then on the other hand, you have robotics, where the physical properties of sound and the information they carry about the spatial environment for mapping, for navigation, for localizing the interesting sound sources. Similarly there, we need to have this kind of spatial sound reasoning. So we already saw a bit about kind of the production or reception of sound by human ears. And I want to talk about that and the kind of the two sides of the spatial effects in audio. So on the one hand, you have the factors from the 3D environment itself. As we saw in the drumming example, this has to do with the geometry of the space, the materials that are in the room. Is there a thick carpet or is it a smooth marble floor? And then the position of the source sound and the receiver and their mutual relationship in space. So all of that will be, what we hear is going to be a function of this. And then, as we saw before, then how we receive the sound from our two ears and the time delay, the intensity of the sounds, and even the shape of our own individual ears affecting exactly how we receive it. And that kind of binaural sensing allowing us to get the spatial information and triangulate for where a source might be. Now, the other important thing as kind of background that we're going to draw on here is the notion of a room impulse response. And so this is a transfer function that says how, as a function of the relative positions of the source of sound and the receiver of the sound, meaning the listener, how does the sound travel about the room? And so this is a 1D function, the room impulse response, that says how that fall off of the takes place in terms of the direct sound initially, followed by early reflections in the room, these green bars, followed by continued reverberations as the sound bounces around the space, and those blue, that longer tail of blue. And so you can think of this as a signature for a room at a given combination of source and receiver positions. We'll be making use of this as we start to model the sound and think about later in the talk, adding and removing the effects of an environment. So in the remainder of this talk, given this kind of context, there's three main things I want to talk about. So first, we'll look at examples in the work. How are we going to learn about the 3D surroundings from not just vision, but also sound? And then we'll introduce scenarios that we care about the effects of these room acoustics and spatial sensing for speech. And then the last part of this talk, I'll broaden that to think about those things in the presence of noisy environments. So multiple sound sources of different forms, and what are those effects going to be, and how do we deal with them? And keeping with the theme, you'll see active elements about what we're doing, and in particular in that third section where we're thinking of how to move around intelligently and have agents, robots that can move so that they can hear the right thing. All right, so let's talk about learning from the 3D surroundings. So what one resource that we put together that actually has helped us do as help us have a platform to do a number of the things we wanted to do here is I'm gonna describe first. This is called SoundSpaces, and what it is an audio simulation platform with very high realism that allows us to attach to simulators and simulate and 3D assets from visual environments that have been very influential in computer vision. So earlier, we had the ability in the field to have good tools for very fast rendering from arbitrary camera positions for now thousands of real world environments that were scanned. So these are 3D models, but they originate from real 3D environments, often captured with things like a Matterport 3D scanner, such that you can start pushing around a virtual camera in these environments. And why computer vision folks were very excited about this is because now you have an ability to explore embodied AI problems, meaning where you have perception in the context of action, a moving agent in these spaces, even if you're not dedicated to working on the hardware of robotics. And so this spurred a whole lot of work on the availability of these visual environments and virtual camera movement in computer vision at that boundary of computer vision and robotics. And so where we came along is to think about, okay, how do we allow you to not just see from arbitrary positions in these real world environments, but also hear how things would sound? And so what SoundSpaces provides is the ability to render sound of your choice at arbitrary positions in any scanned environment, and to do it in real time. And it's highly realistic in terms of accounting for the geometry, the materials, and of course the relative position of the source and the receiver. And the way we do it, kind of over time, we improved our most recent version, SoundSpaces 2, does this in fact on the fly computation. So essentially you're generating the room impulse response, that 1D function, at any given combination of source position and receiver, such that, say if a source was here, now you can, the model can place the receiver at any orientation and position else in the environment. And similarly, more sources as you wish, and put these together so you hear how things would sound if your agent was in any of these positions. So this was something that we contributed to allow this kind of research to take place, not just with vision, but with sound. And I'll play you a sample. To really hear this spatial sound, of course, you'd need to listen to our videos with headphones, so that you would hear the left signal going to your left ear, the right one going to your right ear. So you won't hear the direction of these sounds, but at least we can listen to the intensity changes as we move a virtual camera through this environment. Oh, and I should say, so you'll see the egocentric view, what the agent would see on the left, and just for context for us, the top-down map of this full environment and where the camera's moving as that blue arrow. I hope you can hear it here.
We don't hear anything.
Nothing at all?
No.
Okay.
No, there's peeping.
Yeah, we can hear.
Okay.
There.
Okay. So it may have been, it certainly was quieter at the beginning. There was also a piano playing, like as you pass the piano, so we can embed sound sources with the semantics of the environment and the objects in it. So that's what that example was showing. Maybe we can hear glimmers of it in the room there, but definitely if you're interested, check out these samples online. But the realism is good, and now we have this flexibility to work in these arbitrary spaces. And we've run multiple challenges over the years where particularly for navigation, people can compete on the AV navigation challenge and have leaderboards and so on. And so it's helping some of this progress in a very systematic way. All right, so we have this platform, and I'm going to be telling you next about some things we do with it. And in fact, I'm about to touch on one of the papers that I believe some folks have looked at in the reading group. And this is where we're talking about visual echoes. So to motivate, I'll show you this tiny sample from an old movie called Daredevil, where the character cannot see, but can see or sense the environment by listening to the echoes here, striking a gate, and then listening to the response in order to sense in a very dramatic way what the surroundings are like. Okay, so we want to do this. We want systems, models, representations that obtain the spatial sensing, which would maybe often be done with visual sensing, but to gain this from the audio. And in fact, to do it through essentially echolocation by emitting sounds. We can even emit them actively in order to hear the result, the reaction due to the environment so that we can get those cues. And so our idea with visual echoes is to learn an image representation that will help spatial tasks downstream. And something of note here to keep in mind is we're going to be learning these representations where we can both see and hear, but then deploying them even when we don't have audio, so visual only. And we'll see in just a couple moments the kind of spatial tasks we mean are things like depth prediction, which naturally goes well with the kind of sensing we're talking about, as well as surface normal estimation and even visual navigation, where we need to take an unmapped environment and move through it efficiently.
Can we ask questions on the way? Because there are a couple of questions in the audience right now. Would it be all right?
Sure, yeah, please.
Go ahead.
Yeah, okay. No, it was a very small question at the time. Now we've tried to reach you a little bit. So did you say that you can also estimate the surface material, which has huge impact, I guess, on the sound that's being repelled from it or absorbed? And
Yeah, so can we estimate the materials?
Yeah, do you model the materials of the?
Yes. Yeah, the materials are modeled, and so any surface has attached to it the name of a material with which then there's coefficients in the system to represent its properties, the physical properties, and that's accounted for in the simulation.
Thank you.
And one more question.
And, hi. So you said you run these on the fly, right? Like, isn't that super expensive? Was that learned, or is that like an actual analytic solution? Like, sounds super complicated to me, and sounds
Yeah.
like a lot of computation.
Yeah, and that's, maybe that's why we didn't do it in the first round. The first round, we pre-computed room impulse responses and gave you dense kind of pre-computed ones, so it was a fast lookup. But then in SoundSpaces 2.0, we did upgrade it to do fast rendering on the fly. And so it is a bidirectional ray tracing model and well implemented to allow you to do this very efficiently. Now, the first version is still faster. So like if you're using SoundSpaces 1, you'll sacrifice the precision, meaning the density of this, where you can place the camera and the mics, but it'll be extremely fast. And then if you use SoundSpaces 2, you have a lot more flexibility on placement and continuous positioning around the environment, but at some cost of speed for sure. But still, we found usable for even training the kind of RL models that we build from here.
Super impressive. Thanks.
Thank you.
Great.
Right
Thanks
now,
for the
no
question.
questions.
Okay. Good. So let's look at then the visual echoes. And you can think of this as an example of gaining supervision from the physical world. So by interacting with the world, an agent that's listening to the effects of its emitted sounds is gaining information about it. And this is kind of cool because, this is in contrast to our traditional or frequent forms of supervision that are about humans telling agents or labeling things in images and so on. So sure enough, we can emit sounds and listen to the echoes in SoundSpaces. So here's a kind of visualization of that. Again, the ego camera will move on the left and you'll hear these clicking sounds. It's emitting a frequency sweep and then listening to the results. And on the right is a top-down map of this environment. All those white blobs are big furniture. The blue is the path of the camera and the arrow is where the camera is currently.
We don't hear sound, is that correct?
Now we do.
Yeah, Yeah, I'm sorry you're not hearing it well. It seems like the louder it gets, you find it's audible, but I have my sound maximized. I don't know if there's anything to do in the room to increase the volume, but if
It
so,
was
that'd
like
be
a
great.
great thing. We didn't hear anything, and then it started.
Yeah. Okay.
When you shared
Well,
the screen, you shared sound, I suppose, right?
yep. Yep.
It's not coming through your microphone.
No.
It might just be delayed. It's also true.
It's also true.
I'll try one more.
Now we hear it.
Okay. Yeah, what I'm gathering is once it reaches a certain volume, you can hear, and else you cannot. Well, the thing that I think we can get the feeling from the visualization, even with the soft version. What I was showing on the left is the depth maps for these environments in color. So the color reflects the nearness to the camera, and you are hearing you could hear like the difference in intensity and kind of imagine if you were moving through that space, how hearing that change in the sound would be giving you signals, much as someone who would use echolocation to localize themselves, giving you signals about how close you are to big surfaces. Okay, so, and you could say inspired by Daredevil, not literally, of course, but you could see that parallel. All right, so how do we set up visual echoes for learning the representation? We can take any of these 3D environments, insert our virtual camera and microphones, and capture the echoes we receive, as well as the images we receive. So imagine here in this top down, if you were oriented to the left, and then you would see this RGB visual. You could also measure the depth map, say, and then on the right are 2 spectrograms representing the echoes received for the left and the right ear. And so on. Now you can rotate the camera. You could do the same thing, point it in other directions at that position, and then you could do any of this at any position. So this is kind of, I guess, a first form of active sensing in the spirit of being in the environment and then listening to the results of a sound action. So collect all this data, and now here let's set up the learning problem for the machine. So we want to learn a visual representation, and our key insight is to say that it's self-supervisable, meaning we don't need a human to annotate anything to find out if we can predict the consistency of the echoes in what we see. So if an agent is seeing this RGB first-person view, we'll be learning a visual network to process that, to encode it. And then if the agent is hearing this binaural sound, the question during training is going to be, is that sound consistent? Is it the one that you would hear if you were seeing that RGB view? Or is it something from some other orientation? And so during training through SoundSpaces, we can sample all the orientations. And then as you're putting in training pairs, sometimes you put the right one and sometimes you put the wrong one. And it could be wrong by any offset from the correct one. And so now you can supervise this and train a model that's job is to say, in fact, which of the orientations is it? Is it the right one? Or if it's not, which of the other ones is it? And so this is a self-contained training problem we can do thanks to that data. And what it's going to do, and the key point of this method is that if you're going to be able to decide if these agree, you need to be able to look for those visual and audio patterns that reflect the same geometry and things about or materials in that scene. And so that means you're getting the chance to instill the signal about audio that reveals something about space into the visual representation. So that's the key, really, to link these two so that now our visual representation gets enriched by whatever spatial sensing the audio has to offer. So then I mentioned at the onset, we're going to use this as a visual representation. And, of course, if we have audio sensing, this can enhance at inference time. But the power here, what can be kind of nice about this is we've pushed that audio signal into the visual representation, that visual echo net. And now when you process any new RGB frame, you're getting a representation that has that spatial info. And we showed this by first looking at depth estimation. So in depth, you'd like to have 2 views, but there's great work over the years in computer vision saying even in monocular imagery, we can start to infer depth by learning the associations between depth and even semantics in the environment. And so these depth maps, red is far away and blue is close. And the ground truth depth maps are that second row for the top row of images. This is from a famous data set, NYU, UV2. And then if you were to train a CNN to do this from scratch, you'll get the results just below the ground truth. And if you were to train initializing with our visual echoes representation, who's been enhanced by audio, you get the row on the bottom. And these are more accurate depth maps that are enjoying the benefit of that audio-based pre-training. And what's nice about this result, it really is a sim to real transfer. So, we did train this in the simulated environments from SoundSpaces. They were real world environments, as we know, but the sound itself was certainly simulated. And here we are with real training images from these new environments and able to do something useful. So that's encouraging. And is there a question?
Yeah, just briefly. So one thing maybe I've missed it, is how you map auditory signals onto pixels in that camera frame, basically. I assume there's the camera is always pointing in some direction relative to the sound. I assume those two things I don't know if that's necessary. How do you do that mapping? Basically, I'm trying to understand.
Yeah, sure.
Is it supervised in some way, or does it need a depth signal from a laser camera or whatever?
Yeah. So is the question about the depth maps or about this part of the learning?
Well, in order to map the auditory space signal that you get onto the visual signal, you need to have it in the same reference frame, right?
Mm-hmm.
And I wonder how you achieve that visual reference frame for the auditory signal. I haven't got that.
Yeah, so what they share is the pose of the camera and microphone. So over here, when you place the sensors in this environment, you have the two microphones and for the left and right ear, and you have the camera. And when you're sampling these, you can make them consistent. So you can sample, here's the sound I'd get, here's the sight I would get. And we can do this across the environment. And then when you're over here in training, you're playing with the alignment between that audio and the vision. And so like a training sample in which they agree will just be as we sampled it, and the ones where they disagree would be where we're changing the orientation of the microphones.
Yeah, so you have a ground truth basically, and you're trying to match that.
You have a ground truth about the pose of these two sensors. Yeah. In the SoundSpaces. So we control, keep in mind this is done in, I guess, inexpensively, in the sense that these are pre-computed visual environments, scanned, and now we're just at will moving microphones and cameras.
Okay. Yes, that makes sense. Thank you.
Okay, great. So we did this for depth prediction, surface normals, as well as visual navigation, and kind of there was consistent outcome here where having this pre-training with audio is helping our visual representation. Furthermore, we're even doing things that, here we're at the time competing with or even outperforming heavily human supervised pre-trained representations, famous ones being like ImageNet based pre-training, where you have thousands to millions of images that are hand labeled with the objects in them. So this is good because we're able to, get the value of spatial information into our visual encoders. Now I want to go from here to talk about another aspect of the spatial environment from sound, where we want to say, well, we want to do audiovisual mapping. So we're interested in a floor plan of an environment. And in computer vision, we know how to do this very well. If you take the camera around to enough places, just based on geometry or even learning-based methods to represent that geometry, you can get a full map, 3D, or in this case, we're going to look at projection to the ground plane, so a 2D occupancy map of the environment. But that's if you've seen enough of it. And really what's cool or, intriguing about audio in this setting is to leverage its ability to kind of see where the camera doesn't go. So get broader spatial sensing because you can listen. And and such that even with short camera paths, so the one I'm showing here is these cones in blue are the camera moving, say, across time in this environment we're looking down on. And if you just use vision, you'd map just like some portion of that environment. But the idea is if we're also listening, we're going to expand our ability to map with still these kind of minimal observations. And that happens for two reasons: semantics and geometry. So one, on the semantic side, if you were taking this camera around, okay, and you start hearing someone whisking to your left, or you hear a shower running over here, or a TV and so on, those kind of objects and sound sources will be signatures of the kind of rooms that are around you. And this will carry with it properties about likely sizes and layouts. So that's semantics. And then the geometry, just as before, if I start moving from those initial camera positions on and hear how the sounds are bouncing around, even in rooms emitting near rooms I don't even enter, that'll give signal about how big the spaces are, or how much free space there is behind me. And so that was our idea in this work, was to create floor plans. So get these 2D ground plane maps that either say, simply where is the free space, this black and white map, or even labels on those rooms to say, well, here's the likely kitchen and bathroom and so on. So we're going to infer those from minimal video signals by bringing in the audio as part of this mapping. And what we did here is train a supervised model. So placing, again, we can leverage SoundSpaces for this to get ground truth maps. And then here we're training a multimodal encoder decoder network that pulls in the audio and the visual, and then is trained to decode out into the ground plane map. And to do this over a sequence of observations so that you start stitching together an egocentric map of the environment. So you can imagine training that up, I hope, kind of related to this training setup I showed a minute ago, but now for this ground plane mapping. And what we like is then you get fuller maps with sparser observations. So now my camera positions are shown in these orange cones. And in this 3D environment, if we had taken that camera path and only used the ground plane projections of the depth sensing we could do there, you would get the cyan portion of the map. That's as complete as it would be, and it corresponds also to this bright green portion at the bottom. In fact, the bright green portion goes even further. This is where we use earlier work that does kind of anticipation, learning-based anticipation of other free space based on visual sensing alone. But if you use the audio, you get this much bigger map. The full green overlay on this is the full map we get. And the top right graphic is the bird's eye view, top-down projection, top-down view of that ground plane map, labeled according to where things are correct and where they're missing. So basically, you want this map to look all green and black. It would be perfect. All the places in blue and red are where things are wrong.
One more question.
Yeah, so when you're saying the audio map, then you move a speaker and a microphone with the camera, and you play a certain beep sound, or how do I have to imagine this?
Yeah. Yeah, this is different, actually. This is more passive than the one we just saw in visual echoes. There's no, we're not emitting sounds here. We're listening to the environment. So the more sounds that are in the environment, the richer this information will be.
So you're actually relying on these like semantic cues of a shower or something like that.
Yeah, the semantics and their geometry. So, if we walk by and, whatever the sound, if whatever sounds are being emitted by these objects, yes, the semantics are helpful, especially for room identification. And then the same properties of geometry, this time not from the agent's emission of sound, but sources that are in the environment. And I'll show you an example that might help illustrate that. Although I know, let's see what we can hear for this one. It's gonna play the sounds, the passively observed sounds in the environment, and we'll see again that ego camera moving around, and then the map being flushed out as you hear these sounds. And this is in SoundSpaces. Okay, so in this sample, I hope you could hear, especially as they got louder, the sounds in the environment. We kind of loaded it up with different sounds, like someone was typing, someone eventually was knocking on the door, there was a phone ringing. And as the camera moved through, now as we look at this freeze frame on the right, in orange, the camera moved through. Again, the cyan is what we could map from what we saw in the RGB, and then the broader map in this light green is what we get because of the sound that we're sensing through this learned model. And I wanted to check if from this, if I've answered the question that was here about how this was set up.
Yeah, that makes a lot of sense. Yeah.
Okay.
Maybe a follow-up, and it's a single microphone. It's not like a two-ear kind of simulation thing. It's a single microphone that you move with the camera, right?
Here we're using here too we're using the multi-channel audio.
Okay. Thanks.
Good. So I want to build from here and actually get to a more explicit, even more explicitly active part of this problem. So we started by generating these maps, saying, okay, we get the video, we form the map. We get the video and the audio, we form the map, and now we're really interested in audio not only for what we have just shown, oh, let's see a broader area and let's get cues about semantics. But there's a third thing that audio is great for our AI models, and that is, compared to vision sensing, it's low power. Like it'll consume low power on the device. It's expensive to run the camera. It drains the battery. And so audio is a signal that we could expect more frequently, and we would like to be more stingy with when we use the vision. And so this suggests an approach where the agent, the model that needs to learn to say when it's worthwhile to sample RGB versus when we should just continue listening. And so we took this idea again, in that mapping scenario where we're actually doing this in a multi-camera setting. So there'll be one, there could be one, but more people moving about the environment. And you can imagine, like, this is kind of a setting detail, but, imagine these are people wearing smart glasses and they're talking to each other, or, any other sounds that are there in the environment are still taking place. And so as these two or more subjects are moving around, they can each get a visual stream, they can each get an audio stream. And so here, this is the orange and the blue. And of course, the audio they both receive will be mixed from whatever the other person's sounds are, as well as sounds in the environment. And so, maybe opportunistically, you could say, okay, from any of those sensing streams, you could compute a map just like we were doing before. But the key thing now is, as I've said, to decide when to turn on either of these cameras. We'll always listen, and that's just motivated by the fact that it's a much lower power, less expensive cue to take. So then our job is to decide when do these cameras need to be on or off, or we'll pose this in terms of there's a sequence of movements every time we could be sampling frames. Which ones should we skip? And of course, the whole point is to skip them before you observe them. So it won't be the case that we're not filtering. We're not saying let's listen and then, or look everywhere and then decide which ones not to use. We're saying, okay, before we sample the visual frame, is this really a frame we're going to want to sample? So it's like predictive or active in that way. So we then have those inputs for every view, and then we learn a policy. Here we're addressing this with deep reinforcement learning. So our job is to learn a policy that makes actions. The actions are, do I want to get the next frame or not? And then it'll get rewarded as it's learning this policy, in our case, according to two things. So we want to reward this policy to decide on frame capture based on how much that visual frame improves the map accuracy. So during this training, you get rewarded when a frame taken helps accuracy, and vice versa. And we also do some kind of novelty rewards, saying we'll have a prior to say avoid sampling the same camera pose. So these two or more viewpoints then are being amassed into a shared map. Just think of generalizing what I showed you a minute ago, but now, accounting for the movement of these cameras, you can kind of pool your sensing to get this broader map. And the loss for this map, and the thing that says how accurate are we getting, is based on the the map error. So we have a ground truth during training, and we want to say, like, let's get that as close to that true map, the MIJ and the MIJ tilde, as possible. So let me show you an example out happening here in SoundSpaces. This is getting a little more complex because now we have two sequences of sensing. So maybe person one here took a path like this in orange. Person two in blue.
Veil laconic. It seemed to him that he was already on the other side of the wall, and he no longer
Okay, so we're putting in waveforms to represent the speech of that
hoping
person
that there
and
might
the
be
other.
a change in the weather. In vain. A maidservant entered and saved the situation by offering them a
And then we're, our job was to say which of these things to sample. So those were the complete sequences of what they would see and hear. And then when we run our policy, having learned it, we run the policy, and in this particular instance, it decided to turn on the camera for, I guess, 3 camera positions for the second subject and 1 camera position for the first, leading us to have, okay, these are the RGB views. And I think you can kind of imagine why, yes, of course, there is some redundancy across visual views. So even, baselines that are more spacing out the views could do some reasonable things. And, our job is to even a higher bar to say actively which are the views that are going to matter, condition on what we are hearing. And merging these into a shared map, we'd get a top-down map like the one on the right. Again, the big blobs are the furniture. Like this is this box over here is the long table on the rectangle on the left. And these are color-coded for the occupancy, and we're seeing kind of the agreement against the ground truth. So incorrect predictions are in bright green and gray. All right, so that was an example we're getting, and of course, we're systematically evaluating this, importantly, both in simulation and in the real world. So for this study, we also had real world captures for the audio in the environment and the room impulse responses in the environment, so that we could do exactly what I've been describing in simulation, also with some real world data. And these are what we're looking at are the accuracy, the F1 score, for doing this, first of all, by bringing in the audio to do this in a passive way, because we win by, some edge by bringing in the audio. And then most importantly, here's the active sensing curves, where here you want a curve that over time, as the agent keeps, going, or as these camera steps keep going forward, the accuracy goes up sharply. So you'd like these curves to be sharp early on. And the curves that you're looking at are R's in green, and then alternative policies you could take, like randomly deciding when to turn the camera on, that's in blue, doing it every time you're in a unique pose, which is a smarter way to do, or being greedy, this which is purple. Greedy is where you just use up your visual samples first right away, and then you're left without any later on. And so you can see kind of where that intelligent active sensing, both in the simulation, in the middle plot, and the real world on the right plot, is giving us that advantage of using our money wisely, meaning using our expensive visual frames most wisely. And we can kind of convert that back out to what does it mean for power? That was the motivation here. And you can see we would estimate saving 74 watts of energy per episode, meaning per 16-step sequence in the environment to form a map. Now, these are clearly in development. Failure modes that we observed is when there's too little overlap between the selected views, which as usual will be a challenge for reconstructing the map, or if the agents or any of these baseline policies over-select at the onset, or these aren't robots, these are people in our setting here, so too little motion by the people. Now, in other work that I'm not presenting today, but kind of worth mentioning for its alignment here, we've studied related kind of active sensing of the environment for mapping, but from the agent's point of view, meaning a robotic agent, where there you do control the camera. And so it's not opportunistic about, oh, where are they going to go? Should I see here or not? But rather we can control the robot's positioning in the environment and learn policies for its motion to say, where should you go to get a good map and explore this new space? And at the same time, when should you do audio versus visual sensing? All right, so I want to move next into modeling the effects on speech. And this is a lot of fun, in part for me because of the real world implications. We know we want to understand people speaking in all kinds of places. We want devices that are smart about listening to people. Those places could be noisy, they could be big, they could be small, the person could be close to the mic, they could be far. So we need to do this well. And we also know that people get harder to understand, both for human and machine listeners, because of big acoustic effects. So the more the sounds are bouncing around, the more reverberation is there, it's harder to hear or to understand. And so if we were getting all our speech in anechoic chambers, I guess our machines would be happiest, but we don't. And so really, imagine saying something in anechoic chamber versus saying in a big cathedral, and it's going to be harder and harder to parse out what is being said. So we want to do something about this, and so we'd like to de-reverberate the sound so that we could do downstream things like better speech recognition. And so the idea is, okay, we know that we receive sounds that are basically convolutions of some original source sound, AS, with the room impulse response, and that's what we hear. That's what we receive. Can we strip that away? We would like to de-reverberate, think like basically remove the effects of the room impulse response so that we could only hear that clean source. And of course, if you know the room impulse response, you can do this. And so our job is to try and infer that from the received audio so that we can strip it away. And when we were looking at this task to start, great prior work is there, but it's really audio focused, and you constrain the task, and we come in here saying, well, we know that the visual surroundings, as we've been talking all along today, also influence the sounds that get received. And so if we're looking around as we receive this sound, we ought to be able to do better to infer that room impulse response and remove its effects. So our goal here is to learn to do dereverberation here at single channel audio using both audio and vision. And we did turn to SoundSpaces as well as real data settings to explore this. And so we could go in these 3D environments. We're going to render speech. We're using a data set called Libra speech. It's like people reading different passages in English, and we can generate training data. This is the value of SoundSpaces here, because you have the ground truth. You have the waveform you're inserting, which is AS. You have the acoustified version of that, which is what you're going to receive, AR, and now you can have supervised data to learn how do I get back to the clean source sound and train it by both those visual and audio inputs. And I'm not giving details about the model here, but you can imagine a supervised model that can do this reconstruction. So I'll show you a couple examples. Here's a SoundSpaces one. You're looking at a panoramic view on the left of a person looking down a long hallway, and the speaker, the person, is far away from the camera. And I'm going to jump right to the reverberant speech. Please tell me if you can hear this once I play.
As the chase drives away, Mary stands bewildered and perplexed on the doorstep.
Right.
You're hearing it?
Yeah.
Good. Okay, so that had some reverberant effects of the environment. Here's what our Mased, what's just called Vita, would give back as the clean audio.
As the chase drives away, Mary stands bewildered and perplexed on the doorstep.
So it has removed some of those effects, and it's taking advantage of what that scene looked like. Even able to, when the subject is when the sound is a person, even the fact that they're visually present and how far they are from the camera from that 2D inferred input can help you out in doing this job. Here's a real example. This is in a classroom where we have the ability to place a speaker making these sounds precisely, and then know what the ground truth is. Let me show you that example.
However, that was over now. The tree gone. The story had an end.
Okay, so that's the sound that was received, and here's what we clean up.
However, that was over now. The tree gone. The story had an end.
And I think as these spectrograms show visually, we are cleaning up towards that ground truth sound shown on the left. You could also hear artifacts nonetheless, and that especially in that second sample, showing, or so that you can hear some of these errors, and definitely more challenging in the real environment. But now what happens with, I motivated dereverberation as saying, let's make speech recognition have a better chance. And so let's look at what happens there. Here's an example, the RGB again on the left, and then we'll hear the different versions of the sound alongside, okay, what is the result when you pass those sounds into an automatic speech recognition system?
Two monsters only were creating all this commotion, and before my eyes are two reptiles of the primitive world.
So clean audio, very good ASR, that is correct. Okay, now it becomes reverberant.
Two monsters only were creating all this commotion, and before my eyes are two reptiles of the primitive world.
So same speech, but the word error rate is increased, and you can see those errors in red and the text on my slide. If you did audio,
two monsters only were creating all this commotion, and before my eyes are two reptiles of the primitive world.
Okay, things are actually are better. It's dereverberated. The word error rate starts getting better.
Two monsters only were creating all this commotion, and before my eyes are two reptiles of the primitive world.
Okay, so this is what we want. This is a good example where removing the reverberation helps the downstream task. We can have better clarity. And I'm not going to play this one, but here's another one. Similar idea. And we were measuring all of this, how can we do compared to the reverberant sounds, compared to if we did more traditional audio only dereverberation, or if we took a recent GAN-based speech enhancement approach. And across a few different tasks, I showed speech recognition. We also looked at speech enhancement and speaker verification, all things you want to do with the voice signal. And this is sim to real transfer. I'm not showing the table, like the results are even more controllable, and I suppose margins even bigger when we look at the synthetic or rendered data. And this is taking it all the way to real world data sets where we want to see if we can transfer what's learned in simulation to the real world. Okay, so I want to remind you from here of that first slide I showed, which, this cool video, playing drums, different places, different sounds, to say that, okay, sometimes, like I just motivated, we want to get rid of the effects of the environment because they're actually a nuisance. They're making it hard to do the perception task. But other times we want to keep those sounds. In fact, we want to be able to add them. So why would this be? In terms of virtual reality, augmented reality, we want to have remote presence that sounds very real. And so that I could feel like I'm in your space, or you could feel like you're in my space, because the audio is that consistent with what you're seeing. So that would call for transporting you to a new environment artificially through the sound. So making the sounds match a visual environment. So that's an example. Then in film dubbing, it'd be best if it still sounds like the person speaking in another language is doing it in the setting of the film. So that, again, similar reasons, keep the realism, or even in video conferencing, where maybe I'd like my voice to sound like I'm actually in the Zoom background that I'm using. I mean this hypothetically. The background you see is the background you get with me today. But wouldn't that be neat to have the voice agree? So these are all reasons to want to put the effects of the room. And in the literature and acoustic matching, there's different ways to do this. Generally, it's audio only, done with audio only, and it's done where there's an assumption of access to that target environment. So you could capture audio in the environment and then make the signals match. But what we were proposing is to do what we call visual acoustic matching. And the idea is you could take audio input, source audio, and take an image of a target space. And then say, okay, take that original sound, make it sound like it took place here instead. So this is the task. So audio and image in, audio out. The audio out should sound like, okay, that sound maybe was captured in the environment we're seeing. So you could say, oh, take this piano played in some cozy apartment, and now, okay, re-render it so that it sounds like it's in that big stage. And one of the general things we had to solve to do this, because yes, we can supervise, including with SoundSpaces, to get this kind of data, but we wanted to be able to learn from in the wild video, because that would really open up just the amount of environments in which you could add acoustic effects or learn the acoustic effects of. So for example, YouTube videos where people are in so many different places, you know, even much beyond the thousands that we might be able to load into SoundSpaces. And so we had some insight. We've kept building on this where, you know, the problem is you have the audio in the target environment, but it itself has the room acoustics in it. So how can we start to disentangle so that we can learn even from this kind of data in a self-supervised way? So what we do is take the observed sound from a video like this and then do automatic dereverberation and then corrupt it with some random transformations to the impulse response, such that now we have a source audio that keeps the content of the original sound but has mismatched acoustics. And that's what will allow us to still have some kind of paired data, even from in the wild videos, to train. And we're training this then in a supervised way and with this kind of self-supervised model. I'm not going into the details of this model. I think many of the models I'm showing today are kind of encoder, decoder, multimodal models that allow you to set up the losses to say what you know, of course, say what you care about. In this case, we care about the reverberant sound matching the target audio. So going from the source to the target conditioned on the image as well. Now, what do we get? Let me show you an example or two. Here, I'm going to play
Stuff it into you, his belly counsel.
the original audio, and that's anechoic. And now we'll place it in a few different environments. So first, let's place it in this office.
Stuff it into you, his belly counsel.
Let's place it in the garage.
Stuff it into you, his belly counsel.
And the auditorium.
Stuff it into you, his belly counsel.
And it's surely subtle. That's actually, you know, part of the value of this is like resynthesizing sounds to match the very specifics of the visual environment. But I hope you could hear as we move from left to right, actually greater reverberation to match the properties of the inferred properties of these visual environments. And so in fact, the reverb time's getting longer, and it's, you know, inferring from these environments how the sound would start to be received, depending on that context. And then here, try to make that application scenario I was motivating. You know, imagine you heard the original sound like this.
If a man had stolen £1 in his
But now you want to make it sound like it's coming from a person speaking in the environment here in your mixed reality world. It should inherit the effects of that environment.
If a man had stolen £1 in his
and what the effects of that were, you know, making that sound a bit warmer and close in for it to match that setting. Here, my video conference example, here's the original.
Yea, his honorable worship is within.
And here's the resynthesized.
Yea, his honorable worship is within.
You can see that image revealed kind of more reverberant effects from the size of it, and this, like, it looks like a smooth marble floor, and we hope you could hear some of those effects. And we're able to analyze, quantify, especially thanks to SoundSpaces, but also on the video side with this the YouTube kind of videos that we were using for training this as well. And we've done user perception studies for time. I'm not showing them here. All right, so the final bit, we're gonna close out looking at speech in environments and in noisy places. Okay, so just, you know, adding some confounding issues and talk about that idea of actively moving to hear better. So classic problem in real life and also in AI is cocktail party problem, where you say, I'm in a noisy environment, there's many people speaking, and I need to attend to the speech of someone in particular. So, you know, within that crowded environment, how do we do this? And we've done work on this over the years in, you know, regular 2D video. Here I'll show you an example of what we can do where because we
haven't measured it.
Because we can see the person and also hear their voice, we can start to remove the background sound better. So here's the original.
Nope.
haven't measured it, but it's cut down the noise to a point where we have the right vibe that it's an action kind of place.
So that was the original, and then here we'll play
Haven't
our
measured,
model with
haven't measured it, but it's cut down the noise to a point where we have the right vibe that it's an action kind of place.
And so you could hear that sounds of the background, the dishes clattering, people speaking are muted overall, and you can hear better just the specific speaker there that was who's detected here. So I could call that passive audio visual source separation. We just have a video. There's nothing more we can do about that. We're not going to move the camera, but we can do this kind of source separation. But we got interested in making this active and embodied. And so the idea was, can we let the sound and vision guide our agents to move in a way they can hear better? So, the analogy would be if you're trying to hear something in that cocktail party setting and you start moving your body so that it makes it easier for you. And importantly, that might mean, like a great baseline approach would be just get closer to that sound source. But as we'll see in a minute, the optimal movement behavior is not so simple. And because if you're in environments with big objects like furniture and hallways and multiple rooms, nearness to the sound source is part of the game, but also how you position yourself such that the acoustic effects from those other big objects affect the sound you receive can also help how effective the sound is that you're going to get. So we do this in 3D environments like in SoundSpaces. Here's the problem setting. You are the agent. Sound sources are multiple. So maybe there's a piano at S1, there's someone talking at S2, or some object making noise at S3, and you are this agent, the robot over here, and you want to decide how you'll move. So you could separate some target monaural sound. So maybe you really want to listen to the green thing, the target. How should you move over time so that that's the sound you can best extract and subtract the rest? So we created a method to do this for active audiovisual source separation. I think that the reading group looked at kind of a second incarnation of this work that we did. We first were calling Move to Here, and it's a reinforcement learning agent. And so it's going to learn a policy where its action decisions are about how to move. And so it could, rotate, it can move or left or right, or it can move forward. And over time, it's accumulating these audiovisual observations. And then as it's training in the reinforcement learning setting, the reward it gets is specifically how much did separation improve over time. Here, I mean audio source separation. So it's really just giving us the ability to learn movement policies that help you hear better in the environment. Where hear better is, to be clear, is doing that source separation, extracting that foreground sound. And maybe I should make clear that neither the map of the environment nor the position of the source are given, right? You're just an agent with a camera, with microphone that needs to move around so that you can hear the source the best. So here's an example of that happening. Ego view on the left, top-down map on the right. And as things get light gray, the agent's seeing that and starting to carve out its own inferred map. And so the agent will hear we're calling mixed binaural audio. So mixed meaning all the sources that are there.
Time of our meeting drew nigh. Ralph called on me first, the most common question, without asking me first, during this time to Miss Reed. I had a great respect and affection for her, and had some reason to believe.
So in this example, there was, I guess, an accordion and two people speaking, and our job is to extract one of those target speakers. And so the agent is making decisions about how to move across the environment so that it can best extract that human speaker.
The time of our meeting drew nigh. Ralph called on me first, the most common question, without asking me first, during this time to Miss Reed. I had a great respect and affection for her.
This idea,
drew nigh.
I hope that you could hear that clearer speech kind of like our passive video example, but now, you know, a stationary speaker a human speaker in the room and the robot moving to hear what they're saying more clearly. And like before with the chat to map approach here, we're looking at an active curve for performance. So higher is better for separation quality. And over time, as we move from left to right, we want to see that curve goes up sharply. And again, similar to before, baseline's related to like, okay, other things I could do is just move around randomly. I'd still get some new signal, or I could find new places to move. That's actually the best baseline. Or I could stand there, or I could stand there and rotate around. And so we get some evidence. What we like to see is that by learning the policy, we can make wiser decisions about where to move the mics and camera in order to do better hearing. All right, so for reference, in case there's interest in putting papers, some of which I've touched on today along these different topics for the work we've been doing here. And I want to conclude by thanking you for your attention and highlighting the key authors in the work that I was presenting today, all listed below. And I'm going to stop and be very glad to hear any comments or questions.